Hi, what's up, you guys? So, previously in our previous video, we did question number 1, and today in this video, we'll do question number 2, which is this one right here. Now, in your previous video, we solved our question number 1 using the power series method, all right? And we followed certain steps to be able to solve this question. Now, before I jump into question number 2, I want to do a quick revision of all those steps that we have talked about in our previous video. And the reason why I wanted to do that is because those are the same steps that I'll be using for all the problems in section 4.1. Okay, so it's important that we get familiar with those steps because in these problems, they can be a little tedious to work with. So, and it's also super easy to kind of get lost, kind of lose your track of what you're supposed to do and where you are supposed to be. So, it's a good thing to have like a map, right? Like where your destination is, to which side, which direction are you going to go, so you have a clear picture of what exactly you're supposed to get. All right, so I hope it kind of makes sense. So let's get right into the steps then. So if you remember, the entire idea of this exercise was we need to solve this differential equation using our power series method or approach, whatever you want to call it. So what I mean is whatever differential equation we have in all these exercises, our solution would be in a form like this. Oops. Right, so we have our summation n equal to 0 to infinity a sub n and x minus x sub 0 to the power n. Kind of a little clearer. Okay. Where, like I said, our a sub n and x sub 0 could be any number, right? Now, in this exercise, we are given that we have to find our solution about 0. So when they say about 0, what they're basically saying is that our x naught would be 0. So that gives us our summation from n equal to 0 to infinity, a sub n, x to the power n. Okay, so now when we do our little expansion, we get a sub 0, x to the power 0, plus a sub 1, x to the power 1, plus a sub 2, x to the power 2, and so on. Okay, so the goal is our differential equation has to be in this term where we have to find these coefficients right here. Okay, so that's the entire idea, that we are doing all these steps to be able to find our coefficients. Okay, now in order to do that, we follow certain steps, right? So our first step was that we will be given, we will have our certain power series, right? And then we will substitute our power series expression in our differential equation. Okay, so what are those power series expression? So we already have one, which is this one right here. Okay, let me just highlight this one instead, because obviously the x naught is equal to 0, so we're dealing with the one on the right. Okay, so we already have one of them, and we have seen in our previous question, and we'll also see in today's video and all the questions of section 4.1 that they will have a y prime in it. So that means I have to have my first derivative of y. And we have seen that in our previous video that our first derivative of y is summation from n equal to 1 to infinity a sub n times x to the power n minus 1. Again, when we do our first derivation, always remember our n starts with a 1 instead of a 0. Okay, so again, if we have a second derivation, that means our n will start from 2, okay, instead of 1. Okay, so now we have our y prime as well. So let me highlight that using a green box. I just like colors in my little math workbook. So, okay. So once we have these general power series form, we can substitute that in our main differential equation. And once we do that, we will have multiple power series, right? And then our second step would be to combine those power series into one, highlighting one, single power series. Okay, so we'll have multiple ones and we'll try to combine them to one power series. So we just have one to deal with. Now, clearly we can't just combine them, right? We have to have something in common. So obviously we have to have some conditions to be able to do that. Okay, so let's talk about the conditions. The first condition was that the exponents are powers of x has to match. Okay, so what I'm trying to say is that, let me go back. This right here and this one right here has to be the same. Okay, so it can be, I mean, one of the power series can't just have a power n, the other one can't just have n minus 1. They both have to be the same. Now, which one are we going to take? Are we going to change this one or are we going to change this one? Now, conventionally and specifically like in math, we and it's a common practice to express them as x to the power n. Okay, so we always aim to match the exponents to x to the power n. Okay, so let me write that over here. Okay, again, the reason is because it's just a lot easier. Okay, it's easier to do that. Okay, all right, and then our second condition is that the series must start from the same index, meaning they must have the same starting index. So what do I mean by that? Again, going upwards. So what I'm saying is that this one and this one right here has to be the same. Okay, now just like my previous condition, which one do I change? Again, conventionally, we always try to keep the larger starting index number, okay, and to change the lower starting index number to a larger number. Okay, so for example, if I had if one of my power series was this one and the other power series was this one, so I'll keep this starting index and I'll try to start my power series index from 1 for the first one. Okay, because the n is equal to 1, clearly the 1 is larger, and I will try to make my smaller one to a larger one. Again, it's all conventionally easy to do that. That's the only reason we do that. Okay, all right. So let me write that the bigger starting index. Okay, all right. Then once we have fulfilled those conditions, then we can finally combine them into one, all right? And once we do that, our third step would be to solve for the coefficients a sub n. So we saw previously, we need to solve for this one, we need to solve for these ones, all right? So we need to solve for the coefficients of a sub n. Now, in order to do that, I will going to use my recurrence relation. I should have used a green color for this condition. You know what? I'm gonna just write this. It looks nicer. Okay. It's all about presentation right there. Okay. All right. So that's my third step, that I need to solve for my coefficients. All right. And then once I'm done solving my coefficients, so once they're determined, I can finally write my solution. Of power series, which is basically this one right here. Okay, so these are my steps. Again, let's do a quick revision of this again. First, we will substitute our power series expression into our differential equation. We're just going to plug in our power series expressions into my differential equation. And then we will try to combine them into one. Now, before we do that, we need to make sure that our powers of x is n, okay? And they have the same starting index. So we'll always go for the bigger starting index. That's going to stay, okay? All right. And then our third step would be we need to solve for the coefficients of a's. And then lastly, we will write our general solution of the power series, okay? All right. So these are my 4 steps basically. So once we know what we need to do, all right, we can subsequently like work on them, okay? So let's quickly work on our second problem without wasting any time. So let me write the question first. So we have y prime minus x to the power 3, y equals 4. Okay. All right. So like I said earlier, the first step would be to substitute my general form of power series into this differential equation. So let me write out my power series again. And then I have my y prime, which is n equals 1 to infinity a sub n times x to the power n minus 1. All right. So now we have these two, again, drawing my boxes. Now we are going to plug in these two into my differential equation, okay? So I have my y prime first, so we're going to write the y prime first. So I have summation n equal to 1 to infinity a sub n times x to the power n minus 1. Then I have my minus, right? So I have minus, and then I have my x cube. And then I have my y. So again, substituting them over here. All right, equals 4. Can't forget what I have for my right-hand side. Okay, now the first step is done, okay? Here we can actually simplify that, all right? We have our x cube, we have our x cube on the outside, and we already have 1x on the inside, so clearly we can, distribute that inside our power series, and we can see that they have the same base, right? They both are x's. So according to the rules of exponents, since we have the same base, that means our powers, or my exponents, adds up. Okay, that means it's going to be 3 plus n. So let's rewrite that. So I have summation n equals 1 to infinity a sub n times x to the power n minus 1 minus, then summation n is equal to 0 to infinity a sub n x to the power n plus 3 equals 4. So now we are actually perfectly done with step 2, okay? Now, my next step would be to combine them into one, right? Now, if we look at our exponents, because remember what I said, that in order to combine them, we have to fulfill two conditions. First, that the powers of x has to be the same, which is x to the power n. So if you look over here and here, clearly they're not the same, and clearly they're not x to the power n. All right, so now let's do what Spider-Man from Far From Home tried to do, which was turning these bad boys into good ones. So basically turning n minus 1 to an n and n plus 3 to also an n. Okay, so let's try to do them separately, okay, so that it doesn't get confusing. So let's try to first convert the first one. So I have summation n equal to 1 to infinity. Let me use a darker one. Okay. A sub n times n x to the power n minus 1. And I am trying to transform this to be x to the power n. Now, how do we do that, right? So if you observe carefully, if I look at n minus 1, how can I make it to an n? Clearly by just adding a plus 1 to it, right? So if we just add a plus 1 to it, we can see that it can easily be transformed into x to the power n. Now, in our math rules, basically, if you are adding plus 1 to one of the n's, that means you also have to add plus 1 to all my n's in my power series. Okay, that's involved inside the power series. Okay, so that means my n, this n right here, will now become n plus 1. And my another n, which is this one right here, becomes a sub n plus 1. Now, again, as per rules of the power series, if all my n's increases by 1, then my starting index decreases by 1. So now it's going to become 0 to infinity. Okay, so let's repeat what I said. Okay, if all my n's in my power series increases by 1, then my starting index decreases by 1, or any other number. So if it has increased by 4, then my starting index would have decreased by 4. Okay, and vice versa. Okay, so let's not forget about the vice versa. So it also works for decreasing part. So if all my n's has decreased by 1, then my starting index would have increased by 1. Okay, and we'll see that in a second. Okay, so just to be clear, I'm going to write this over here, that since n's increased by 1, starting index decreased by 1. Okay, all right, so first job done. Okay, first job of transforming them is done. Okay, then I'm gonna work on the second one, on trying to transform the second power series, which is this one right here. Okay, all right, so let's go ahead and do that. So I have my summation n is equal to 0 to infinity a sub n times x to the power n plus 3. Okay, now I am going to do the same thing that I've done for my first one. I will try to convert this n plus 3 to x to the power n. Now, how do I do that? Again, if I just subtract 3 from this, then my positive 3 and negative 3 gets cancelled, just like my positive 1 and negative 1 has gotten cancelled. So then we are left with x to the power n, right? So just by subtracting 3 from my n plus 3, I will get an n. So since I've subtracted 3 from the power of x, which has involved an n, that means all my other n's also decreases by 3. So that means my other n is basically this a sub n. So that also decreases by 3. Now, remember what we said in this statement right here? That since all my n's has increased by 1, starting index decreased by 1. But here, since all my n's decreased by 3, then the drum roll, starting index would increase by 3. Okay, so that means now n will be equal to 3 instead of a 0. Okay, so we have successfully transformed our exponents to x to the power n. So let's quickly write that over here. So now our new transformed power series is from n equal to 0 to infinity, a sub n plus 1 times n plus 1 times x to the power n. Then I have a minus. Then summation n equal to 3 to infinity, a sub n minus 3 x to the power n equals 4. So we can see that our starting index, our powers of x it matches, and it is x to the power n. Now, do you think we are done yet? Well, I sound like Dora the Explorer, but just answering you, we're not. Yes, and why do you think is that? If I look in my starting index, they are not the same, right? They are different. So our second condition was that we want to transform these into the same starting index. Now, which one do I pick? Again, we said that we always keep the bigger one, okay? We always keep the bigger one. That means we are going to keep our n is equal to 3, okay? So n equal to 3 stays. That means I will try to level up n equal to 0, okay? So let's do that. So I want to start my first power series from n equal to 3 to infinity. Then I have a sub n plus 1 times n plus 1 times x to the power n minus summation n equal to 3 to infinity, a sub n minus 3 x to the power n equals 4. Now, since I started from 3, so what happens to the first 3 terms, right? What happens when n is equal to 0? What happens to n equal to 1? What happens to n equal to 2? Yes, so now if we do not include that, clearly this is going to be lost, and this is not how we want it to be. We cannot lose any of the terms because it's part of this, right? So what we can do, we can explicitly write them separately, okay? And add them in these terms, okay? So let's write for n equal to 0. So when we plug in n equal to 0 over here, we get a sub, so let me write that over here. So n equal to 0, we get a sub 0 plus 1 times 0 plus 1 times x to the power 0, which is basically a sub 1. And then when it's n equal to 1, then I have a sub 1 plus 1 times 1 plus 1 times x to the power 1, which is 2 times a sub 2 times x. And then when I have my n equal to 3, I have a sub 2 plus 1 times 2 plus 1 times x to the power 2, which is 3 times a sub 3 and x squared. So these are the 3 terms that we want to write them separately, okay? Since we want to start our index from 3, so and we don't want to lose them, so let's write them separately. So I have a sub 1 plus 2a sub 2x plus 3a sub 3x squared plus, and then the rest of my summations, my power series. Okay, so now we can finally see that we have fulfilled our two conditions, right? We have our powers, x to the power n, and they match just fine. And our starting indexes are also the same. That means I can finally combine them, all right? So let's go ahead and do that. So I have my a sub 1 plus 2a sub 2x plus 3a sub 3x squared plus summation n equal to 3 to infinity. Now, we have our x to the power n as common, so let's take that as common, and let's write the leftover terms. So I have a sub n plus 1 times n plus 1 minus a sub n minus 3 equals 4. All right. So we finally and successfully completed step 2, okay, which was basically combining them to 1. All right. Now we have done that. So now we're going to move on to our step 3, which basically was to find these coefficients right here. Okay, now we want to know these coefficients. All right. Now, in order to find these coefficients, let's observe what we have on our right-hand side. Okay. Now, on our left-hand side, we have our first term, which is a sub 1. Okay. And if you observe carefully that our a sub 1 is just a constant number, right? It has no x attached to it. Okay. Now, if I look at my right-hand side, we just have a single number, which is a 4. And again, this 4 doesn't have any constant to it. So clearly, these two matches just fine. Okay, they don't have any x's. Okay, all right. So that means my a sub 1 equals 4. Okay. Now let's look at our second term, which is 2a sub 2x. So I have 2a sub 2x. Now let's look at my right-hand side and let's check if I have a coefficient for x power. Okay, and if I look on my right-hand side, clearly there is no x's, right? There is no coefficient for x. That means this entire thing is a 0, which basically means that our a sub 2 is 0. Okay. Then let's look at my third term, which is 3a sub 3x squared. Again, let's look for the coefficient for x squared. And if you can see, there is no coefficient for x squared. There's just a single 4 number. That means this is also a 0. Hence, our a sub 3 is also a 0. So we have finally found our coefficients for a sub 1, a sub 2, and a sub 3. Okay? Just by looking at what I have at my right. Okay? Just by observing it. Okay? All right. So done with our first 3 coefficients. Now we have these coefficients right here. Now we need to solve for these. Okay? Again, let's go back to the idea of looking at what I have on my right. Okay? Now, this series right here, it's applicable when n is equal to 3, right? So I'll have my coefficients for x to the power 3, for x to the power 4, x to the power 5, x to the power 6, and so on and on. And let's look at my right. Do I have any coefficients for x to the power 3 or x to the power 4 or x to the power 5 and so on and so on? Obviously not, right? Just like for my a sub 2 and a sub 3, we do not have any coefficients for any of my n powers, right? So that means this entire thing is a 0. Okay, so let me write that. Okay, which is 4 and 3. Okay, so again, we can see that we found all of this just by looking at what I have at my right. And I can see at my right, I just have a constant value, right, which is a 4. Okay. All right. So now let's generate some terms, right? Because my question was that they want us to generate certain terms and write our solution, right? And we have seen that our solutions can go up to n, but in our textbook, they just wanted us, in our exercise, they just wanted us to generate the first 5 terms and we're good to go. Okay, so let's generate some terms. Okay, so I have this expression for the condition that my n will be greater than or equal to 3. So let's now generate those terms, okay, for n equal to 3 and all the numbers. Now, before we do that, let's isolate our a sub n plus 1. Okay. Okay, I don't need the brackets. Whoops. Just a little bit right here. Okay. All right. So you're say 4 and greater than or equal to 3. Okay, so let's now generate some terms. So when our n is equals to 3, then I have a sub 3 plus 1, which gives us a sub 4, which is a sub 3 minus 3 divided by 3 plus 1. So I have a by 4, a sub 0. Now, I don't know what my a sub 0 is, so I'm going to deal with that later, okay? So let's just take this in our head for 1 second and just let's continue with the terms, okay? All right. Then I have n is equal to 4. So I have a sub 4 plus 1, which is a sub 5. A sub 5 equals a sub 4 minus 3 by 4 plus 1, which is 1 by 5, a sub 1. And I've seen that my a sub 1 is 4. So I'm just going to write 1 by 5. Okay. Then I have n equals 5. So I have a sub 5 plus 1, which is a sub 6, equals a sub 5 minus 3, and 5 plus 1, which is 1 by 6, a sub 2. And I have seen that my a sub 2 is 0. So that's why I have 0. All right, then let's do n equal to 6. So I have a sub 6 plus 1, which is a sub 7, equals a sub 6 minus 3 by 6 plus 1, which is 1 by 7, a sub 3. Again, we have seen that our a sub 3 is also 0, which gives us a 0. Okay. Then let's do n equals to 7, which is a sub 7 plus 1, which is a sub 8, equals a sub 7 minus 3 by 7 plus 1, which is 1 by 8, a sub 4. And if I look, my a sub 4 is 1 by 4 times a sub 0. So I have 1 by 4 times 1 by 8 times a sub 0. Okay. Then let's do n equals 8. So I have a sub 8 plus 1, which is a sub 9, equals a sub 8 minus 3 by 8 plus 1, which is 1 by 9, a sub 5. And if I look, my a sub 5 is 4 times 1 by 5. So I can write 4 times 1 by 5 times 1 by 9. Okay. Then we have our n equals 9, which is a sub 9 plus 1 equals a sub 10, equals a sub 9 minus 3 by 9 plus 1, which is 1 by 10, times a sub 6. And if I look, my a sub 6 is a 0. That means this is also a 0. Then I have my n equals 10. So I have a sub 10 plus 1 equals a sub 11, equals a sub 10 minus 3 by 10 plus 1, which is 1 by 11, and a sub 7. And I've seen that my a sub 7 is also a 0. Okay. Then we have our n equals to 11, which is a sub 11 plus 1, equals a sub 12 equals a sub 11 minus 3 by 11 plus 1, which is 1 by 12, a sub 8. So if I look at my a sub 8, which is this one right here, so I have 1 by 4 times 1 by 8 times 1 by 12, a sub 0. Now, I don't know about you, but I can clearly see a pattern, okay? Like before I was all clueless about what exactly is happening, right? Because like my a sub 1 was 4, then my a sub 2 was a 0, my a sub 3 was also a 0, and then again I have my a sub 4, which is 1 by 4, and then there's a very new unfamiliar a sub 0, which was not there at all. And then again, for my a sub 5, I have 4 times 1 by 5. So I was like, I don't know if there's any kind of series that gives out such random values like that, right? And honestly, I was thinking that maybe I'm doing something wrong. But as I'm moving forward, I do see, you know, like things to kind of fall into places, all right? Let's do another term and hopefully you'll see what I'm seeing too, okay? All right. So I have n is equal to 12, just a sub 12 plus 1 equals a sub 13, and a sub 12 minus 3, 12 plus 1, which is 1 by 13, a sub 9. And then if I look at my a sub 9, which is this one right here, so I have 4 times 1 by 5 times 1 by 9 times 1 by 13. Yep, so now I know how my series and my sequences are. So for you to see that, let's quickly write out all the terms, okay? So I have my general solution, okay? So first I had my a sub 0 because that is the lowest term, the smallest term, right? And obviously I have my a is x to the power 0, which gives out 1, so I don't have to write that. So I'm just gonna erase this. And then I have my a sub 1, which was 4 times x, plus a sub 2, which was a 0, x squared, plus a sub 3, which is also a 0, so x to the power 3, plus a sub 4, which was 1 by 4, a sub 0, so I have 1 by 4, a sub 0, let's not forget the power 4, and then I have my a sub 5, which was 4 times 1 by 5, so 4 times 1 by 5, again, can't forget my power, and then I have my a sub 6, which was 0, x to the power 6, plus a sub 7, which is this one, so I have 0 x to the power 7. Then I have a sub 8, which is 1 by 4 times 1 by 8, a sub 0 x to the power 8. Plus then I have my a sub 9, which is 4 times 1 by 5 times 1 by 9, x to the power 9. Then I have again, a sub 10, which is a 0, x to the power 10. Then I have a sub 11, which is also a 0, x to the power 11. Plus, then I have my a sub 12, which is 1 by 4 times 1 by 8 times 1 by 12 times a sub 0, x to the power 12. And then plus I have my a sub 13, which is 4 times 1 by 5 times 1 by 9 times 1 by 13, x to the power 13, and so on. Okay, now if you look closely, we have our zeros, right? We have a lot of zeros in these general terms. So let's just get rid of the zeros. They're not necessary, right? I just wrote that just for you to see it. So now that we have seen how it looks like, let's just get rid of the zeros and make it a little smaller. So I have a sub 0 plus 4x plus 1 by 4 a sub 0 x to the power 4 plus 4 times 1 by 5 x to the power 5 plus 1 by 4 times 1 by 8 times a sub 0 x to the power 8 plus 4 times 1 by 5 times 1 by 9 times x to the power 9, then plus 1 by 4 times 1 by 8 times 1 by 12 a sub 0 x to the power 12. And finally, I have 4 times 1 by 5 times 1 by 9 times 1 by 13 x to the power 13, and so on. All right. So if you can observe that we have our a sub zeros, right? Out of all the coefficients, the only ones that we haven't found was a sub 0, right? We were able to find our a sub 1, we were able to find a sub 2, a sub 3, a sub 4, and the rest of that, right? But the only ones that we haven't been able to figure out was basically our a sub zeros, which is still there in our alternate pattern, right? So what exactly is my a sub 0, okay? And why can I find this? Now, a sub 0 in this case is an arbitrary number. That is, it could be any number, okay? And how do I find that? Okay, simply if we had our initial value, that is, whoops, y 0. Okay, if we had that initial value, then we would have actually had our a sub 0 value as well. Okay, since we do not have that, there's no answer to what our a sub 0 value could be. It could be anything, so it's completely arbitrary. Okay, now in our question, it asked us to find the first 5 terms, and if you look, we have actually gotten our first 5 terms, which is this in this red box right here. Okay, so these are my first 5 terms that our textbook wanted us to include. Now, we have more, as you can see that we have more terms. Well, I was almost done, right? Right after I found my a sub 8, I was done, right? But then why did I keep going on, right? Why did I keep on finding my a sub 9, a sub 10, a sub 11, a sub 12, and so on? And the only reason behind this was just to show you guys a pattern, right? This is a very interesting pattern that I thought, you guys might find interesting too. So in order to see the pattern, let's do one thing. Let's just make it easier for us to see that. Let's separate our a sub zeros, okay? So I have, like I said, a sub zeros in alternately. So I have 1 plus 1 by 4 sub 0 x to the power 4 plus 1 by 4 times 1 by 8. Oh, I already have a sub 0. I don't have to include that. Whoops. Little boo-boo mistake. Okay. 1 by 4 times 1 by 8 times x to the power 8 plus 1 by 4 times 1 by 8 times 1 by 12 x to the power 12, and so on. And if you look, okay, I hope this makes it clear, we can see that we have a multiples of 4 over here, right? So we have our 4. When we multiply it with 2, we have an 8. And then when we multiply it by 3, we have a 12, right? So we can see that as we go on, we are having our multiples of 4, okay? And in the terms that doesn't have my a sub zeros, which is basically these ones right here, okay, you can see they also have something in common, which is a 4, right? If you can see, all of them has a 4 in the numerator, okay? So I can take this 4 out. Now, you can also see that they have an x common too, okay? So you can either pull out the x as well, or you can keep the x inside the bracket. It's totally up to you, just based on your preference, okay? So I just want to take the 4 out, okay? I want to include the x inside my bracket. Again, you're more than welcome to pull out your x out as well, okay? All right. So if I do that, I have plus 1 by 5 x to the power 5 plus 1 by 5 times 1 by 9 x to the power 9 plus 1 by 5 times 1 by 9 times 1 by 13 x to the power 13, and so on. And if you look in this part of this series, you can see that in my denominator, instead of having multiples of 4, we are adding 4 to my 5s, okay, to the respective numbers. So I just have a 5, and then I kept adding 4s to it. So when I add 4 to my 5, I have a 9. When I add my 4 to my 9, I have a 13, and so on and so on. Again, this is just to show you guys a pattern, okay? This is not necessary in this exercise. Like I said, you were done right after you were able to generate the first 5 terms, which is inside this box, in this red box, okay? So this was my solution for question number 2. Hopefully this helped. Hopefully you enjoyed watching this video as much as I enjoyed making it. And I will see you in the next one. All right, bye-bye.